Hi, my name is Kate Roberts, and I'm a junior at Kalamazoo College in Kalamazoo, Michigan. I'm presenting research which was completed through a Research Experience for Undergraduates program at Michigan State University virtually this summer. This project involved collaboration with Davidson College's Alpha Group, which stands for Algorithms for Learning in Physics Applications. My research focused on developing a new method of processing data to track particles within a detector known as the Optical Parallel Plate Avalanche Counter, or O-PPAC. The detector is a small, thin, square box with the upper and lower sides of the box being made of electrodes, or thin conducting foils, which allow rare particles to pass through them and have an electric field between them. They have a separation of a few millimeters, hence parallel plate in the name, and connecting the two sides are 4 equal-length walls made of collimated photomultipliers, or photon-detecting diodes. To take a measurement of a rare particle, a source of americium is suspended above the O-PPAC, and as ionizing alpha particles pass through the conducting foils and into the gas, they release energy in the form of electrons and photons. This process repeats over time thanks to the electric field between the foils, and it's called an electron avalanche. The goal for the new method of data processing for particle location was to decrease the amount of time required to process data as well as increase the accuracy. So I spent my summer learning how to code in TensorFlow and by extension Python in order to create a machine learning method with which I could accomplish my goal. I ended up writing code for a dense neural network regressor, which is essentially trained by accepting simulated data in the same format of real detector data. The data is a single line of numbers, with values ranging from 0 to 300 or more, and it simply gives the number of photons each diode detects along each wall of the detector. So you'll have a peak on each side where more photons are detected, and 4 peaks in total across the entire row of data, which give the location of the particle. The simulated data is simply a cleaner version of the real data, and it has the added perk of the real particle location associated with the data row as well. So the traditional method for finding location involves splitting the data into the 4 sides of the detector, and then fitting Gaussians to all 4 sides, which, as you can imagine, takes a good chunk of time when you have 300,000 data points. Having a known particle location is imperative to training the neural network for real data. With the locations, the neural net makes guesses as to what it thinks the x and y location should be, and then it compares that guess to the real value. Depending on how off the guess is, it then adjusts variables within the dense regressor to make its values more accurate. With more training and more data, the model becomes very precise. My final results actually ended up being plus or minus 0.03 millimeters in the x and plus or minus 0.04 millimeters in the y, which is significantly more accurate than the original plus or minus 1.4 millimeters for x and y. So my hopes are that these values can hold up against the real data, which will be tested later this month, and I'm very excited about that. Thank you to everyone at Davidson College, MSU, and FRIB who made this research possible. I would not have been able to do anything close to this without them. So thanks again.